Hi everybody, today I'm going to give an overview of how the Jeffcott Rotor model project progressed over the semester. So first we started with looking at the history of how it began, starting with the first analysis of a spinning shaft and the conclusion that the whirl amplitude increases without bounds, to the discovery of a second critical speed, which then was confirmed by Jeffcott and which he incorporated into his model, which included damping in the system. So the Jeffcott rotor model is a flexible spinning shaft that spins at a certain shaft spin speed, and it has a rigid disc mounted on it. And this shaft spins around a bearing axis at a certain whirl frequency, and the amplitude of this whirl frequency can be determined by the equation of motions in the system. So the Jeffcott rotor model makes an assumption that since it has 3 degrees of freedom, x, y, and theta, since it's spinning at a constant speed, the torsional vibration can be neglected, and we can look at just the two transverse directions, which have two equal orthogonal natural frequencies. And so, using these equations of motion, we used computer software to solve solutions for the Jeffcott rotor model for for each of its parameters, and so that we can adjust these parameters and view the system response um, for different conditions, for different initial conditions in the system. And through this process, we understand the history, the importance, uh, the concepts behind the Jeffcott rotor model, the math behind it, as well as how to code it with capability of changing parameters and viewing different system outputs.